Physics E. The physics of the atom. Models of the atom. 1.1 The work done by scientists such as Thomson, Rutherford, Bohr, and Chadwick played a crucial role in establishing the modern view of the atom and advancing our understanding of atomic structure through the development of atomic models. J.J. Thomson proposed the first atomic model in 1898, known as the Thomson model or the plum pudding model. According to this model, the atom is a sphere with a positive charge uniformly distributed throughout, and electrons embedded within it. Thomson's model suggested that atoms were indivisible, with no distinct central structure. Ernest Rutherford, along with his students Hans Geiger and Ernest Marsden, conducted the Geiger-Marsden experiment, also known as the gold foil experiment, which provided significant insights into the structure of the atom. In this experiment, they bombarded a thin gold foil with alpha particles and observed their behavior. Contrary to Thomson's model, Rutherford's observations were unexpected. Most of the alpha particles passed through the foil undeflected, indicating that the atom is mostly empty space. However, a small number of particles were deflected, suggesting the presence of a concentrated positive charge in a tiny region called the nucleus. Rutherford's model described the atom as having a dense, positively charged nucleus at the center, with electrons orbiting around it, much like planets around the Sun. Niels Bohr made further contributions to atomic theory by proposing the Bohr model in 1913. This model incorporated the concept of quantized energy levels or shells, in which electrons could reside. According to Bohr's model, electrons occupy specific energy levels or orbits, and they can transition between these levels by absorbing or emitting energy in discrete amounts. The Bohr model successfully explained the stability of atoms and the emission spectrum observed in atomic spectra. James Chadwick's work in the early 1930s led to the discovery of the neutron. Chadwick demonstrated that in addition to protons, the nucleus of an atom also contains neutrons, which have a similar mass to protons but carry no electric charge. The presence of neutrons in the nucleus helped explain the stability of atoms and the variation in isotopes. Overall, these scientists made significant contributions to the development of atomic models, providing insights into the structure of atoms, the presence of a dense nucleus, the arrangement of electrons in energy levels, and the existence of neutrons. Their work laid the foundation for the modern view of the atom and our understanding of atomic structure. 1.2 The Geiger-Marsden experiment, also known as the gold foil experiment, played a crucial role in establishing the nuclear structure of the atom. Conducted by Ernest Rutherford, Hans Geiger, and Ernest Marsden, this experiment provided key insights into the composition and arrangement of particles within the atom. In the experiment, a beam of high-energy alpha particles, helium nuclei, was directed at a thin gold foil. Surrounding the gold foil was a circular, fluorescent zinc sulfide screen. Whenever alpha particles struck the screen, a tiny flash of light was produced at that point. The results of the experiment were unexpected and led to significant conclusions about the structure of the atom. Most of the alpha particles passed straight through the gold foil with minimal deflection, indicating that atoms are mostly empty space. However, a small fraction of the particles experienced significant deflection, suggesting the presence of a concentrated positive charge within a tiny region of the atom. From these observations, Rutherford made the following conclusions about the structure of the atom. 1. Most of the space within an atom is empty since the majority of the alpha particles passed through the foil undeflected. 2. The deflection of a small fraction of alpha particles indicated the presence of a concentrated positive charge. This led to the proposal of a dense, positively charged nucleus at the center of the atom. 3. The nucleus contains most of the mass of the atom, as the vast majority of alpha particles passed through the foil without interacting with the nucleus. 4. Electrons, with their negative charge, surround the nucleus and move around it in specific energy levels or orbits. The Geiger-Marsden experiment provided crucial evidence for the nuclear model of the atom, challenging the previous notion of a uniform positive charge throughout the atom proposed by Thomson. Rutherford's model, based on these experimental findings, described the atom as consisting of a dense, positively charged nucleus and orbiting electrons. This experiment revolutionized our understanding of atomic structure and laid the foundation for subsequent atomic models and theories. Structure of the atom. 2.1 The structure of atoms is a fundamental concept in chemistry and physics. By visualizing the arrangement of electrons, protons, and neutrons within an atom, students can better understand the overall organization and distribution of charge within the atom. This visualization helps us grasp the composition and behavior of matter at the atomic level. 2.2 In terms of mass and charge, electrons and protons have distinct characteristics. The electron is a subatomic particle with a negative charge and a relatively small mass. On the other hand, protons carry a positive charge and are much more massive than electrons. Comparing the mass and charge of these particles provides insight into their relative importance and effects on atomic properties. 2.3 Atoms are typically neutral and stable entities. This is due to the balance of positive and negative charges within the atom. The proton, which carries a positive charge, is balanced by an equal number of negatively charged electrons. As a result, the overall charge of an atom is neutral. This balance of charges contributes to the stability of the atom and its ability to form bonds with other atoms. 2. For the relationship A equals Z plus N is a fundamental concept in atomic notation. Here, A represents the atomic mass, Z represents the atomic number, which corresponds to the number of protons, and N represents the number of neutrons in the nucleus. By understanding this relationship, students can represent a nuclide using standard notation, which provides information about the composition of the nucleus. 2.5 Isotopes are atoms of the same element that have different numbers of neutrons. While the number of protons, and therefore the atomic number, remains the same, the varying number of neutrons results in isotopes with different atomic masses. Isotopes exhibit similar chemical properties due to their identical numbers of protons and electrons, but they may have different physical properties due to their varying masses. 2.6 The shell model of the atom is closely related to the periodic table. Each element in the periodic table has one more proton than the element preceding it, which determines its atomic number. The atomic number dictates the number of electrons in a neutral atom of that element, and these electrons are distributed in shells or energy levels around the nucleus. The arrangement of electrons in the shells contributes to the element's position in the periodic table and its chemical behavior, as elements in the same group often exhibit similar properties. Radioactivity. 3.1 Marie Curie, a renowned scientist, made significant contributions to the field of radioactivity. Her work was instrumental in the discovery and understanding of this phenomenon. Curie, along with her husband Pierre Curie, conducted groundbreaking research on radioactive substances, particularly on uranium and its compounds. They discovered two new elements, polonium and radium, which exhibited strong radioactive properties. This discovery not only expanded the periodic table but also provided evidence of the existence of previously unknown radioactive materials. Marie Curie's work also involved investigating the properties of radiation emitted by radioactive substances. She coined the term radioactivity and developed techniques to measure radioactivity accurately. Her pioneering research laid the foundation for the field of nuclear physics and radiation therapy. 3.2 Radioactive emissions can be classified into three types: alpha, beta, and gamma radiation. Each type has distinct properties and characteristics. Alpha particles, alpha, are composed of 2 protons and 2 neutrons, making them identical to helium-4 nuclei. They have a positive charge and are relatively large and heavy. Due to their size and charge, alpha particles have a limited range and are easily stopped by a few centimeters of air or a sheet of paper. They have low penetrating power but can cause significant ionization and damage when absorbed by living tissue. Beta particles, beta, are high-energy electrons, beta, or positrons, beta+. They have a negative charge and are much smaller and lighter than alpha particles. Beta particles have a higher range and penetrating power compared to alpha particles. They can pass through a few millimeters of aluminum or a few centimeters of water. Beta particles cause ionization and can penetrate living tissue, but their ability to cause damage is lower than that of alpha particles. Gamma rays, gamma, are electromagnetic waves of high energy and short wavelength. They have no charge or mass, making them highly penetrating. Gamma rays can travel long distances through air, penetrate several centimeters of lead or several meters of concrete. They cause ionization and can pass through living tissue, potentially causing damage. Gamma rays are the most energetic and dangerous type of radiation. 3.3 Experiments comparing the ranges of alpha, beta, and gamma emissions help understand how these emissions interact with matter and the differences in their penetrating power. Alpha particles, due to their large size and positive charge, have the shortest range. They can be easily stopped by a few centimeters of air or a sheet of paper. Beta particles, being smaller and having a negative charge, have a longer range compared to alpha particles. They can pass through a few millimeters of aluminum or a few centimeters of water. Gamma rays, being electromagnetic waves, have the longest range and can penetrate several centimeters of lead or several meters of concrete. The penetrating power of these emissions can be attributed to their ability to ionize atoms and interact with matter. Alpha particles cause ionization through direct collisions with atoms, while beta particles cause ionization through both direct collisions and electromagnetic interactions. Gamma rays primarily interact through electromagnetic interactions, including Compton scattering and photoelectric effect. 3.4 The tracks of radioactive emissions in a cloud chamber provide visual evidence of their movement. A cloud chamber is a device filled with supersaturated vapor, typically alcohol or water vapor. When a radioactive particle passes through the chamber, it ionizes the vapor along its path, causing condensation to occur. This condensation forms a visible track that can be observed and studied. Alpha particles leave dense and distinct tracks in a cloud chamber due to their large size and strong ionization. The tracks appear as thick, straight lines. Beta particles, being smaller and having less ionizing power, create thinner and less defined tracks that may be curved. Gamma rays, being uncharged and highly penetrating, do not leave tracks in a cloud chamber. The observation of tracks in a cloud chamber played a crucial role in early studies of radioactivity, allowing scientists to visualize and study the behavior of radioactive emissions. 3.5 Alpha and beta particles, as well as gamma rays, can be affected by magnetic and electric fields. Alpha particles, having a positive charge, are deflected by both electric and magnetic fields. In a uniform magnetic field, alpha particles move in curved paths due to the Lorentz force. The direction and radius of the curved path depend on the particle's velocity, charge, and the strength of the magnetic field. Beta particles, being negatively charged electrons or positively charged positrons, also experience deflection in electric and magnetic fields. The deflection of beta particles depends on their charge and the direction of the magnetic field. In a magnetic field, the paths of beta particles curve in a direction determined by the charge of the particle. Gamma rays, being uncharged, do not experience significant deflection in electric or magnetic fields. They continue to travel in a straight line unless they interact with matter through scattering or absorption. 3.6 Nuclear reactions, such as alpha decay and beta decay, can be represented in standard form using specific notation. Alpha decay is a nuclear process in which an alpha particle is emitted from the nucleus of an atom. It can be represented in standard form as follows: Rn plus He, where R represents the parent nucleus, Rn represents the daughter nucleus, and He represents the emitted alpha particle. Beta decay involves the emission of a beta particle from the nucleus. There are two types of beta decay: beta minus decay, beta, and beta plus decay, beta plus. Beta minus decay can be represented as follows: Cn plus E, where C is the parent nucleus, N is the daughter nucleus, and E represents the emitted electron. Beta plus decay can be represented similarly, with the emission of a positron, E plus, instead of an electron. The standard notation for nuclear reactions provides a concise representation of the processes occurring during radioactive decay. 3.7 An activity can be conducted to demonstrate the random nature of radioactive decay. This can involve performing experiments that yield a radioactive decay curve or using analog demonstrations like throwing dice or tossing coins to illustrate random processes. One way to demonstrate the random nature of radioactive decay is by using a simulated radioactive decay experiment. By starting with a fixed number of radioactive particles and measuring the number of remaining particles at regular intervals, students can observe a decay curve. The decay curve shows a random pattern of decay over time, with no predictable pattern for individual particles. Analog demonstrations, such as throwing dice or tossing coins, can also be used to illustrate random processes. By assigning a rule, such as heads represents decay and tails represent survival, and repeatedly tossing the coin or rolling the dice, students can observe the random nature of radioactive decay. Each toss or roll represents the decay of an individual radioactive particle, and the overall trend demonstrates the statistical behavior of a large sample. These activities help students understand that radioactive decay is a random process, and the decay of individual particles cannot be predicted with certainty. 3.8 The decay process in radioactive substances is independent of external conditions. This means that radioactive decay occurs spontaneously and is not influenced by external factors. Regardless of the conditions external to the nucleus, such as temperature, pressure, or chemical environment, the rate of radioactive decay remains constant. This property is known as the half-life, which is the time it takes for half of the radioactive substance to decay. The independence of radioactive decay from external conditions is a fundamental characteristic of radioactive substances. It allows scientists to accurately determine the half-life and predict the decay behavior of radioactive materials under various conditions. 3.9 Graphs of random decay demonstrate that radioactive processes have constant half-lives. The concept of half-life refers to the time it takes for half of the radioactive material to decay. In a graph of radioactive decay, the number of radioactive particles or the activity of the substance is plotted against time. As time progresses, the number of particles or activity decreases exponentially, following a characteristic decay curve. The half-life is the time required for the quantity of radioactive material to reduce by half. The graph of radioactive decay shows that the rate of decay remains constant over time, regardless of the initial amount of radioactive material. Each half-life represents a consistent percentage decrease in the quantity of the radioactive substance. This constancy allows scientists to make predictions about the remaining amount of radioactive material at any given time. Understanding the concept of half-life and its constancy over time is essential for calculations involving the decay of radioactive substances. 3.10 The concept of half-life can be applied to solve problems involving radioactive decay. Students can use this concept to calculate the amount of radioactive material remaining or the time it takes for a given amount to decay. To calculate the remaining amount of radioactive material, the initial amount, the half-life, and the elapsed time need to be known. By using the formula n equals n0 asterisk, 1/2, caret, tt12, where n represents the remaining amount, n0 represents the initial amount, t represents the elapsed time, and t12 represents the half-life, students can determine the remaining quantity. Conversely, if the remaining amount is given, students can calculate the elapsed time using the formula t equals t12 asterisk log 2, n0 n, where n represents the remaining amount, n0 represents the initial amount, t represents the elapsed time, and t12 represents the half-life. These calculations allow students to understand the decay behavior of radioactive substances and make predictions about their future quantities. 3.11 Radioisotopes, due to their radioactive nature, have several useful applications in various fields. In medicine, radioisotopes are used as tracers to diagnose and treat diseases. They can be injected or ingested by patients, allowing medical professionals to track their movement within the body. By using imaging techniques such as positron emission tomography, PET, or single-photon emission computed tomography, SPECT, doctors can visualize organ functions, detect abnormalities, and identify diseases. In industry, radioisotopes are utilized for various purposes. They can be used to test the integrity of materials, detect leaks or blockages in pipelines, measure flow rates, and determine the thickness of materials. Radioisotopes also find applications in sterilization processes, such as the sterilization of medical equipment and food preservation. Carbon dating is another significant application of radioisotopes. By measuring the amount of carbon-14, C14, in organic materials, scientists can determine the age of ancient artifacts, archaeological findings, and geological samples. Carbon dating relies on the known decay rate of C14, allowing researchers to estimate the time since an organism died. These applications demonstrate the practical significance of radioisotopes in various fields, ranging from healthcare to industry and historical research. 3.12 The release of energy in a nuclear reaction is related to a change in mass, as described by Einstein's equation, E equals mc squared. This equation illustrates the conversion of mass to energy in processes like nuclear fission and fusion. In nuclear reactions, a small fraction of the mass of the reactants is converted into energy. This occurs due to the binding energy of the atomic nucleus. When the nucleus undergoes fission or fusion, the resulting products have a lower mass than the initial reactants. The missing mass is converted into energy according to the equation E equals mc squared, where E represents the energy released, m represents the change in mass, and c represents the speed of light. Nuclear fission involves the splitting of a heavy nucleus into two or more smaller nuclei. The mass of the products is slightly less than the mass of the original nucleus, resulting in the release of a significant amount of energy. Nuclear fusion, on the other hand, involves the merging of two light nuclei to form a heavier nucleus. Again, the mass of the resulting nucleus is slightly less than the combined mass of the original nuclei, leading to the release of energy. The relationship between mass and energy in nuclear reactions is a fundamental principle underlying the immense amounts of energy released in processes such as nuclear power generation and nuclear weapons. 3.13 The utilization of nuclear energy has both arguments for and against it. Factors such as cost, environmental impact, waste disposal, and safety contribute to the pros and cons of nuclear energy. Arguments in favor of nuclear energy often highlight its potential to generate large amounts of electricity without relying on fossil fuels. Nuclear power plants produce a significant amount of energy and can operate continuously for long periods without greenhouse gas emissions. Nuclear power is considered a low-carbon energy source, potentially helping to mitigate climate change. On the other hand, arguments against nuclear energy point out concerns about its cost and potential risks. The construction and maintenance of nuclear power plants can be expensive, and the disposal of radioactive waste poses long-term challenges. Safety is also a significant concern, as accidents or malfunctions at nuclear facilities can have severe consequences for both human health and the environment. The potential for the proliferation of nuclear weapons is another concern associated with nuclear energy. Public opinion on the utilization of nuclear energy varies, reflecting the complex nature of the issues involved. Policymakers and societies must carefully consider the pros and cons of nuclear energy when making decisions about its implementation.